Hello everybody. Today's lesson we are going to look at an exercise called other expressions for acceleration. So previously we have seen that acceleration A is dv dt, or acceleration is the second derivative of position. So these are two formulas that we have seen already for acceleration, and today we're going to look at two other expressions for acceleration. So they're listed here in this purple box. That acceleration equals v multiplied by dv dx, and the other expression we're going to look at is acceleration equals d dx of a half v squared. Okay, so realistically now we actually have four expressions for acceleration, the two in red and these two new ones here. The proof of where these two new formulas come from is written below here. You don't need to actually know where the formulas come from, but if you are interested in looking at that, feel free to read the rest of this page. It's really just using the chain rule to develop the first formula up the top, and then using that one you can develop the one below that. But if you are interested, feel free to read that. Okay, so the question really becomes now is, if you've got four different formulas for acceleration, you'll need to, when you're solving a problem involving acceleration, you'll need to pick the correct version of the formula to use to solve the question. So realistically, you need to understand which formula to use and when to use it. So I've created a nice summary here that you can use and look back at if you need to eventually. So it's got three dot points here that basically tell you exactly what you should be using, which version of the acceleration formula you should be using. So if you're given acceleration as a function of time, so a equals f of t, then you should use a equals dv dt, or a is the second derivative of position with respect to time. Okay, because that means if the original acceleration function is a function of time, then it makes sense to use dv dt because that's a function of time, and dx dt again because you're differentiating with respect to time. Your acceleration could be a function of x. So if that is the equation you're given, then the best version of, or the best formula to use for acceleration is this one here, d dx of a half v squared. Okay, so that's when acceleration is a function of x. If acceleration is a function of v, then you could use one of these two formulas here, dv dt. Okay, so we would use that one if the initial conditions are given in terms of t and v to match these two variables like dv dt. Okay, or we could use this final formula for acceleration. Acceleration equals v multiplied by dv dx. And of course, looking at the derivative, it's a derivative of v with respect to x. So we would use this one if the initial conditions are given in terms of v and x. Okay, so we've got four formulas now, and you can use this summary to help pick the correct version of the formula that you should be using. And basically from here on in, you're solving differential equations as well. Okay, so let's have a look at the first exam question here from 2011. It says a body moves in a straight line such that its velocity v meters per second is given by v equals 2 times the square root of 1 minus x squared, where x is meters and is the displacement from the origin. It says the acceleration of the body in meters per second squared is given by one of these five formulas. Okay, so we go we go back here, okay, and look at this function here, okay, now, and try and match it to something we've got here. Now, we actually do know one thing first, that acceleration equals, so let's try this formula here, v dv dx. Why are we trying this one here? Because do I know v? Yes, I have a function v. Okay. Is it possible for me to calculate dv dx? Well, when I go and look at this equation here, yes, it is possible because I have a function v and it's in terms of x. So I can work out dv dx and I know what v is. It's equal to this equation here. Okay, whereas the other ones don't work. So could I actually calculate dv dt? So I have a function here with v, but there's no variable t. So I can't use that formula. Okay. Could I work with this first one here? Sorry, the second one. Do I know v? Yes. Could I square it? Yes. And then multiply it by half? Yes. And then could I find the derivative with respect to x from this equation? And the answer would be yes, I could, because v is a function of x. So I actually could use this or this function here. Both of those would be correct to use. Okay, so I can actually use either one of those because it's possible for me to work out all of that information. Okay, so let's even go with the first one, a equals d dx of a half v squared. So a equals d dx of a half v squared. Okay, so d dx. So I just work out what's in the brackets. So a half multiplied by v squared. So if I square all of this function, okay, square both sides to give me v squared equals all of this squared. It's going to be, I have to square the 2, so it'll be 4 multiplied by, and the square and the square root will cancel out. So it'll be 4 bracket 1 minus x squared. Okay, and I just multiply the half and the 4 together to give me d dx equals 2 bracket 1 minus x squared. And we now just need to find the derivative of the expression inside here with respect to x. So d dx of, let's expand the brackets, 2 take away 2x squared, and the derivative of that function with respect to x is minus 4x. So E is my answer. Okay, multiple choice, I can circle E, but I could have used the other formula as well. Okay, I could have used A equals V dv dx because I have enough information. I know what the function V is and I can work out dv dx. So either formula works. Okay, and we have our answer of minus 4x. So that's problem number 1. Problem number 2 from 2015. 4-mark question, so quite a lot of marks. Average was 2.8. It says the acceleration a meters per second of a body moving in a straight line in terms of velocity v is given by a equals 4v squared. Given that v equals e when x equals 1, where x is the displacement of the body in meters, find the velocity of the body when x equals 2. So here we've got a as a function of v, and initial conditions are v and x. So if I go back up to the summary, up here, so a is a function of v, so I'm looking at the third dot point here, but the initial conditions are v and x. v and x. So I'm going to use this version of the formula here, a equals v dv dx. Okay, so I write that down. A equals v dv dx. So I replace the letter A in the actual question where it says A equals 4v squared. Replace that with v dv dx. Okay, so therefore v dv dx equals 4v squared, because v dv dx is another way of saying acceleration. So here I'm going to divide both sides by v. I'm going to get rid of this v in the front of the dv dx by dividing the left side by v and the right side by v. So I will get dv dx equals 4v. Okay, now the question is asking us to find the velocity. Find the velocity of the body when x equals 2. Okay, so I actually want an expression for v, which means I need to integrate. I've got dv dx, I will need to integrate to get an expression for v. But carefully looking at this differential equation, I'm going to have to flip it to be able to do that. So I've got to write dx dv equals 1 over 4v. And now I integrate both sides with respect to v, which gives me x equals the integral of 1 over 4v dv. Okay, so I did need to flip this one. I can integrate this function quite easily. I could take out the quarter, and then it's just a quarter times the integral of 1 over v, which is log e of the absolute value of v plus c. And I use my initial conditions. When v is e, x is 1. So x is 1, v is equal to e. So that will give me log e of e. Log e of e is 1. Okay, so it's multiplied by 1 plus c. Rearrange that equation. C will be 1 minus 1/4, which is 3/4 for the value of c. Okay, now I write my differential equation. So I go back up here where I had the plus c. I substitute the new value of c in here. So x equals 1/4 log e of the absolute value of v plus 3/4. Okay, so that's an expression for x in terms of v. The question is asking, what's the velocity of the body when x equals 2? So I can just substitute x equals 2 and solve for v. Okay, so when x is 2, I need to solve this equation. So 2 equals 1/4 log e of the absolute value of v plus 3/4. So we need to do a bit of algebra here. I need to subtract 3/4. Okay, and then I will need to multiply by 4 as well. So I'll need to get rid of the quarter by multiplying by 4. So 2 is the same as 8 over 4. 8 over 4 minus 3 over 4 is 5 over 4. And then 5 over 4 multiplied by 4 will give me 5 equals log e of the absolute value of v. To get rid of the logarithm of base e, I do e to the power of both sides. So e to the power of 5 equals the absolute value of v. Okay. And I then need to think about the sign of the velocity here in this question. Okay, so for the initial conditions to work properly, I actually need to have the positive version of this. So remember, the absolute value means you could have a positive answer or a negative answer. But for everything to work, I actually will need to take the positive version. So the velocity when x equals 2 is e to the power of 5. Okay, so this is a typical question here where you get an acceleration formula. You'll need to pick a version of acceleration, one of the 4. Okay, one of these 4 here has another way of writing acceleration. You can use the summary to help you pick the correct one. And then most likely you'll be solving a differential equation just like we were here. Putting some initial conditions in and answering the required problem, okay, which was finding the velocity when x equals 2. And the last problem we have here, it's an exam question from 2013. So it says a particle moves in a straight line such that acceleration is given by a equals square root of v squared minus 1, where v is the velocity and x is the displacement. It says given that v equals root 2 when x equals 0, the velocity v in terms of x. So it's very much like the other problem, okay, we just did. So acceleration is a function of v. The initial conditions are v and x. So again, if I go to my summary, acceleration is a function of velocity. Initial conditions are v and x. So I have the option of using v dv dx. Okay, would be a suitable option there. Or I believe it's possible to use this one as well. But either one will actually work. So it will be up to you which version of the formula you would prefer to use. But I'll go by what the summary says. So the summary says if a is a function of v and the initial conditions are v and x, we should be using acceleration equals v dv dx. Okay, that's what the summary tells us, so let's go with that. Not forgetting that we need to find v in terms of x. Okay, so instead of writing the letter A in the question, I'm going to write v dv dx. So it will be v dv dx equals, it's the square root of v squared minus 1. Okay, and again here I can divide both sides by v, which gives me dv dx equals, and this will be v squared minus 1 all to the power of a half, instead of writing it as a square root, all over v. Okay, and then from here what we would normally do is do some integration. Okay, so we integrate here with respect to x, but there's no x's on this side, so that means we would need to flip this dE. Okay, so we'd need to do dx over dv equals v over square root of v squared minus 1. Now I can integrate both sides with respect to v, and that will give me x equals the integral of v over square root v squared minus 1 dv. Now, unfortunately here, to be able to determine this antiderivative, you would have to use a substitution technique. You would have to let u equal v squared minus 1. Okay, so this will actually be quite a nasty problem if you go down the route of using v dv dx. So it can still be done. You can still find the antiderivative of this. But it does become much easier if you use the other version of the acceleration formula, the half d dx of a half v squared. It does become a lot easier. So continuing on with this one, we have to let u equal v squared minus 1 du dv equals 2v. Okay, and which implies a half multiplied by du dv equals v. The reason why I've rearranged that for v is because there's a v on top of my integral up here. Okay, so now I can rewrite my integral as x equals the integral. So instead of writing the v on the top, I write a half du dv. Okay, now I'm going to bring the half out the front because constants can come out the front. And then on top of the fraction, it's du dv all over square root of u dv. Now here the dv's are going to cancel. Okay, so I'm going to have x equals a half times the integral of u to the power of negative a half du. Okay, so I now do the integration. So x equals a half multiplied by, so here we're just adding 1 to the power, which is u to the power of a half, and then dividing by the new power, 1 over the new power. So 1 over a half is 2. So it'll be 2 u to the power of a half plus c. And I can simplify that to x equals u to the power of a half plus c. Substitute the u back in. So x equals square root of v squared minus 1, sorry, v squared minus 1 plus c. And I can use my initial conditions, v equals root 2 when x equals 0. So when x equals 0, v is the square root of 2. So square root of 2 squared becomes 2. 2 take away 1 is 1. Square root of 1 is 1 plus c. So c equals negative 1. Okay. Therefore, x equals square root v squared minus 1. Sorry, c is minus 1. Take away 1. But the question asks for what's the velocity in terms of x. So I now have to rearrange this equation for v. Okay, so let's think about that before we approach it. So we're going to add 1 to both sides, which will be x plus 1. Then I will need to get rid of the square root. So I'll do that by squaring. Okay, both sides. So on the left side, I've added the 1. I square both sides. I will then need to undo this minus 1. So I will be adding 1. And then I will need to undo the square that's on the v. So I will need to take the square root of all of that. So there's my answer for v. v equals the square root of x plus 1 squared plus 1, all inside the square root symbol. And if I go back up here, that is option D. Just written slightly different with the placement of the plus 1. Okay. So there's a lot of work in this question just for 1 mark. And you can see that you will have to include different techniques for solving differential equations. Okay, so in problem 2 here, we had to flip the dE. And in number 3 here, we had to flip the dE as well, but we then also needed to use a substitution technique. Okay, so quite a lot of work for a multiple choice question. But this is how we can use what's called the other expressions for acceleration. So there's 2 new expressions here, the v dv dx or d dx of a half v squared are 2 new expressions for acceleration.